Now let's talk about projections. We have a vector projection of B onto A, so I'm just going to draw you a picture. So maybe this is some point P, and I have some vector, maybe over here is Q. And maybe I'm going to take this vector right here, I'm going to call it PR, maybe I'll call it B. And I want to just project it onto vector PQ. What that means is I think about dropping a perpendicular down, drawing a triangle. I end up with a new vector right here. That's like PS. In the same direction as PQ. Just want to point out I can do the same thing if my picture looks like this. Maybe I have P, and maybe I'm projecting B this way now. This is B. I can still draw my perpendicular and extend this backwards. In this case, I have a vector S right here, PR, that will point in the opposite direction of PQ. So this new vector in red is called proj of B onto A. So let's say vector PQ is A, then the projection of B onto A is this piece right here, and that should not say R, that should say S. So the projection of B onto A is also PS. So this creates a new vector when we do this. That's the vector projection of B onto A. We may also talk about something called the scalar projection of B onto A, and this is the magnitude of the projection vector. How long is it? How long is the little red, the new red vector? Sometimes that's called comp of B onto A. So let's look at what that is. It's just the magnitude. So if I look at my picture again, and I have P, S, and Q, and this is R. This is theta. I know this was the magnitude of B. So I know that cosine theta equals this length right here, which we said was the scalar projection of B onto A, divided by the magnitude of B. So if you're solving for the scalar projection of B onto A, you're going to get magnitude of B cosine theta. Now some textbooks don't talk about this scalar projection of B onto A. Some textbooks just refer to this as the magnitude of the projection. So I'm also going to say that, the magnitude of the projection of B onto A, or I could also write it with single bars. That's magnitude of B cosine theta. Means the same thing. Some books just call it some comp. Length of the shadow of B. So we can rewrite A dot B using this, some of this here. So A dot B we know was magnitude of A times the magnitude of B cosine theta. But we just said magnitude of B cosine theta was the comp or the magnitude of the projection. So I can write this as magnitude of A times this, or magnitude of A times the magnitude of the projection of B onto A. So whichever notation your textbook uses means the same thing. Rearranging this, I can solve for comp of B onto A, which is the scalar projection, and I get A dot B divided by the magnitude of A. What I did was take this piece and solve for comp of B onto A. So if I want the vector projection of B onto A, it needs to be a vector, if you look back at this, in the same direction as my original vector A. This was A, remember? In the same direction as A. And it needs to be of magnitude, this little red part, not the whole magnitude of the original A, but the magnitude of the like the length of the shadow. So I can write this as comp of B onto A times vector A divided by the length of A. Why would I do that? Well, this is the length I want right here. This is the length I want. So we have to divide by the length of A to make sure that we have a vector of the length we want. I can write this as A dot B divided by the magnitude of A times vector A divided by the magnitude of A. So you see it's the same thing as doing A dot B divided by the magnitude of A squared. And remember, all of this will be a number. This is a scalar times the magnitude of A. So let's reiterate this. This is the length of the new vector. And this gives a unit vector in the direction of A. Here's an example. Find the scalar and vector projection of B, which is vector 1, 2, and A, which is vector negative 2, 2. So I'm going to do the dot product. A dot B. Well, that's going to be what? Negative 2 plus 4, which is 2. Okay, and then I need the magnitude of A. And this said A onto B, you would do the magnitude of B. Because we want projection of B onto A, and the length of that, B onto A. So magnitude of A is what? Square root of 4 plus 4, which is square root of 8, which is 2 root 2. So the length of my vector projection, which I can call comp of B onto A, or I can do as the magnitude of this, is A dot B over magnitude of A, so that's 2 over 2 root 2, which will be 1 over root 2. Okay, so that's the scalar projection. The vector projection of B onto A is the scalar projection times this unit vector in the direction of A. So I get 1 over root 2 times A. Well, A was negative 2, 2, divided by the magnitude of A, 2 root 2. So we end up with negative 2, 2 is the vector, and we end up with what? A 4 on the bottom? So we get negative 2 over 4 and 2 over 4, which is negative 1/2, 1/2. Why do we care? We can define work as force times distance, but this only applies when work is directed along the line of motion of the object. So let's draw a similar picture to the one we had a minute ago. Here's P, and here's Q, and maybe have a ramp or something. So maybe my ramp is at angle theta, and I am trying to push an object up this ramp, but I want to travel this distance d. So maybe there's a force acting in this direction. I can think about doing the same thing with my vector and scalar projections. I want to move the object from P to Q, and D is the displacement vector. PQ. So you see that force is pointing in a different direction than the line of motion. Another example would be like pulling a wagon. My wagon moves from P to Q, but the angle of the handle is PR. So my work equation is going to be magnitude of F times cosine theta times the magnitude of my displacement. Looking at the pictures, that seem reasonable. This part right here is the component, the scalar projection, but the component of F along D. This part right here is the distance traveled. So if we rearrange, we see that work is magnitude of F times the magnitude of D cosine theta. Let's try an example. A wagon is hauled 9 meters by a constant force of 300 newtons applied to an angle of 28 degrees to the handle. Find the work done. So there's our picture. We have a dad pulling his son in a wagon, and we want to find the work done. So the displacement will be 9 meters, and this dad is pulling with a force of 300 newtons. That's the magnitude of the force. Theta is what, 28 degrees? Find the work done. So work is going to be 9 meters times 300 newtons times cosine 28 degrees, which is approximately 2384 newton meters, is the same as 2384 joules, which is a unit for work.